So let's maybe sort of finish this part by writing down an expression, rewriting the expression for our partition function. Yeah. Or if you prefer, in terms of temperature. Okay. Did I get this? Yeah, it seems to be. Wow, I did the math right, I think. Yeah. Any questions? So that's the main work. I mean, just to take a step back, I think thinking in terms conceptually, drawing pictures is very helpful. That's how you create the grand canonical ensemble. The partitions are permeable. So we wrote down our constraints. We solved for the unknown multipliers. We had an expression for the partition function. And the only thing that we had left to evaluate, because we did the work last chapter, was the unknown multiplier gamma. And we had to go through song and dance, but basically we set up an expression for the differential of log C and related that expression after we massaged it to a thermodynamic expression. And that led us to two things. One was an expression for the unknown multiplier in terms of the familiar mu, chemical potential. And the other was an expression for entropy in terms of the grand canonical partition function. So now we have two expressions for entropy, one in terms of the grand canonical and another in terms of the canonical partition function. So in a sense, there's nothing new here, really. But we did get this new unknown multiplier. Any questions? Okay. I think I want to make sort of two side notes. We've done the major work. I want to talk about really a minor point, but I want to relate the unknown multiplier and the chemical potential to the concept of activity. And then I want to come to what is the characteristic function for the grand canonical partition function. We saw that the Helmholtz energy, A, was the characteristic function for the canonical partition function. What about the grand canonical? So I want to talk about, think of those two things. So first, this concept of activity. Remember way back to thermodynamics, we said the chemical potential can be expressed as, this is convention, this is really just convention, as some reference chemical potential. You have to choose your reference state. For gas, it's usually 1 bar, and it's a fictitious reference state. It's 1 bar, and intermolecular interactions turned off, as if you were an ideal gas. But it's a very well-defined thing. Now we have the unfortunate coincidence of A representing, in this case, the activity and formerly an occupation number. So don't get confused. This is the activity, not the occupation number. And this is the familiar thermodynamic expression. Of course, we used R because we think in terms of large quantities. I'm going to write the same thing now in terms of K. And I'm not going to worry about the mole, the factor of 6.022 times 10 to the 23rd. You can convert from molar to molecular quantities. I'm not going to worry about it. Okay, but we've obviously just done some proportioning here. Okay, so that's fine. And you may remember the activity, all of the non-ideality is contained in the activity. So generally to obtain an activity you have to accurately, you actually have to make experimental measurements. For a gas, the activity was equal to the fugacity. For a substance in solution, the activity is usually the concentration times an activity coefficient. So we might say the activity is equal to some activity coefficient times the concentration in terms of molal concentration divided by unit molality, for example. Just ringing the bell, trying to ring a bell here. Okay, so that's cool. So the point I want to make is that we express the chemical potential in terms of a reference in the activity where the non-ideality is. And the numerical value of A depends on what you choose as your reference. It's one thing if you choose molar reference, it's a different thing if you choose molal, it's a different thing if you choose mole fraction. Just what your reference is. Okay. If we want, we can, for convenience, define implicitly I'm going to stick in molecular terms. Where I think of lambda as an absolute activity. In this sense, suppose that we chose our reference such that it was 0. So suppose that we chose our reference chemical potential is 0, then the chemical potential would be equal to kT times the log of something, right? And that something then we call, well, that's an absolute activity. Okay, we'll rearrange. All I've done is change terms. So sometimes we think in terms of lambda instead of in terms of mu, and in other words, in terms of the absolute activity. And if we do that, we can express C. Okay? Where the power of n comes from the n here. Yeah. I just rewrote it over here. Now, I'd like you to notice that if I want to, I can rewrite C in terms of Q, the canonical partition function. Remember that the canonical partition function depends on J, but N is not allowed to vary. So really, the sum over states J, that's just a canonical partition function, right? For Q of N, V, T. So we now have a relationship between the grand canonical partition function and the canonical partition function. Well, if you like, so that's kind of cool. And we can take this one step further. Remember, for the microcanonical ensemble, we talked about the degeneracy of states for a particular n number of particles and a particular v and some particular energy. Now, when I formed the partition function for the canonical ensemble, thus far we've been summing over J, where J is an individual state. We know that each state, we know that particular energy levels will have a degeneracy. So we speak of the degeneracy of a particular energy level as omega. So if we like, instead of summing over states, we could sum over energy levels. Each energy level, in this sum, each energy level is repeated omega times. So if we sum over the levels, we simply have to multiply each exponential by omega. So this is kind of cool. We can think of the grand canonical partition function as a sum over canonical partition functions, each one weighted by lambda to the n. And we can think of omega as the partition function for the microcanonical ensemble. So the partition function for the canonical ensemble is a sum over the partition functions for the microcanonical ensemble, each weighted by this exponential term. Okay. The only difference here is whether you're summing over states or levels. So you have to be very careful about whether you're specifying states or levels. So that's kind of cool. I think it's even useful to take the time to draw a picture. So let's first draw a grand canonical ensemble. Etc. In general, something like that. Now, each of, let's see, how do I want to put this? So let's consider, so the grand canonical ensemble consists of a whole set of systems with varying E's and varying N's with constant V's. And if you consider a particular, let's change this to an I. So there will be some of these systems for any particular n, call it n sub I. Pick one value of n. There will be a whole set of systems in here that happen to have that n, coupled with any possible set of the e's, e sub j. So you can think of the grand canonical ensemble as consisting of a subset of canonical ensembles. And in fact, this subset, each possible canonical ensemble is going to be represented in the grand canonical ensemble. So in other words, if you consider all of these, you really have so this is now a canonical ensemble. So the grand canonical ensemble is a super ensemble of canonical ensembles. And similarly, we have lots of different, in the canonical ensemble, lots of different values of E present. Any particular value of E will be repeated many times in this canonical ensemble. Right? So E sub j, for a particular j, will be repeated many times for a fixed n and a fixed v. So if you just reach into that canonical ensemble and take out all of the systems that happen to have a particular value of E, what do you have? A microcanonical ensemble, right. So each of the different ensembles can be thought of as a sub-ensemble of the other. They're all related. You can take this one step further. Remember that in the, according to we found that there's one distribution that is maximally represented, right? In fact, it swamps all of the others. So that distribution for the grand canonical ensemble will correspond to one particular canonical ensemble that is maximally represented. In fact, you can forget about all the others. In the canonical ensemble, there's going to be one distribution that is the maximum distribution, maximally represented. It will swamp all the others. That corresponds to this microcanonical ensemble. So what we will find in the end, if we go to bulk systems, is that we can really work in terms of any ensemble. We can choose it according to convenience. What are we holding constant? What's most convenient for us? In the limit of infinitely large systems, these different ensembles, remember their conceptual constructs, really become equivalent. I skipped my characteristic function. I'll come back to that. So we can do it. Um, So you remember that the Helmholtz energy is related to, is just proportional to log Q. So we say that the Helmholtz energy is the characteristic function of Q, because the one is just a constant times the log of the other. So we can ask the question, is there a similar characteristic function for the grand canonical partition function? And the answer is yes, and I want to show you what it is. It's going to be easiest to do that, to write down our expression for entropy. That's what we had before. So this is the entropy in terms of Xi. And I want to manipulate this a little bit.
You're missing the entropy,
Yeah. That's it. Actually, yeah, that's the way I like. I'm going to think this way. I multiply by 2. There. Okay? Okay, it's just algebra. I multiplied by t, and then I brought mu in to one side and everything else on the other. Yeah. Now, remember that certainly for a pure substance, mu times n is just equal to the Gibbs energy G, thermodynamically. Okay. Remember that thermodynamically, is the partial of G with respect to n. I'm thinking now on a molecular basis instead of on a molar basis. If this is a pure substance, of course, yeah, so that's it. So here we go. Now remember that G is equal to thermodynamically U minus Ts plus PV, the Legendre transformations between internal energy and free energy. We've already made this relationship here between average energy over the quantum states and the internal energy. This is just Ts. So kT log C must be equal to PV. So within our characteristic function, it's actually this product of simpler functions. The product, PV, is the characteristic function of the grand canonical ensemble. So, all of the thermodynamic functions can be written in terms of Xi, and there's a big table, I think it's 3-1 in your book. Since none of us likes to do work, right? None of us likes to do derivations if we don't have to. Here's this wonderful table with lots of the relationships just written out for you, right? You've seen it, right? For each of the ensembles, right? And there are more. You can derive more if you want. But, Page 58, table 3-1. So there's S for the microcanonical ensemble. S is there for the canonical. S is there for the grand canonical. Oh yeah. So we've talked about, at this point, 3 different ensembles, but you can imagine more. We're not going to go through the relationships or massage any of the others because the idea is just the same. But there are others. You just hold different things constant. Probably the most useful one that we've not discussed yet is the isobaric isothermal ensemble. So if you were to hold constant not volume but pressure and temperature, and you could hold constant N or mu. I don't remember how they usually think. Oh, it'd be mu, of course, because it's the characteristic. G is the. Yeah. If you were to hold constant mu P and T, you would have the isothermal isobaric ensemble. Where isobaric, baric refers, of course, to pressure. Okay. The conventional symbol for the isothermal isobaric ensemble's partition function is delta. So delta depends on. And as you can imagine, now let's do it in terms of K. T. If you were to go through the whole song and dance, you would write down a picture like this, but allow the volumes to vary. So you'd have not only ensembles with different ends and different energy levels, but also different volumes go through the same thing. You'd have yet another unknown multiplier called epsilon. I suppose you already have alpha, beta, and gamma. Now you have an epsilon. And you would find that epsilon is related to pressure. Okay. Well, this turns out to be a minus up here. And so on and so forth. You can devise other ensembles, but all become equivalent in the limit of very large systems. So I think that's about it. So next time we will go on to the second part of the chapter. We'll pick up with section 3-3 and discuss fluctuations. So, and I'll be happy to take questions at the beginning of the chapter. Class period.